I think we can get started. So, I'm Shiva, and I'll be talking about cloud security and something to do with serverless environment. I'm also joined by my presenter Nimish, and we'll dive deep into our today's agenda. Next slide. So we'll talk about the serverless attack surface. We'll cover some economic impact of the serverless breaches we see around. We'll also do a case study of a sample AI workload with serverless environment, and then have the final takeaways and best practices. So to begin with, let's take a moment and look back at how the evolution has happened in the industry from the bare metal era to the serverless shift what we see today. So to begin with, the 2000s, we still had a lot of mainframes, on-prem data centers, racks of physical servers, and we still continue having that. It's not that we don't see them around, but the evolution has happened where now we see more ways in which the infra is coming up. This is something we call the evolution of infrastructure abstraction. And what we saw in 2000s to 2010s is the evolution of virtual machines. And in 2006, we had the launch of EC2, where we could now start running multiple workloads in one server. And that's when the hypervisors started becoming active. In 2013, we had the launch of Docker. And the very next year, we had the launch of Kubernetes, which now made our applications more portable. And we call that the container revolution, also free SaaS. And finally, we're talking about the serverless, where we have a lot of event-driven workflows. We have stateless functions, and this was made possible by the launch of Lambda in 2014 by TTPs. Now, talking more about serverless attack surface. So this chart here shows different categories of the attack we have. And to begin with, when we say serverless, we are talking about event-driven environment. And the very first one here says the trigger and event source risk. Now, we talk about insecure API gateway configuration, talk about event injection, or let's say the inputs are not validated. Now, what are the risks associated with that? We have data exfiltration, DB or a possibility of remote code execution. Now, similarly, we have another class of vulnerabilities which are related to functional level vulnerabilities. And here we see some of the examples as, let's say, have vulnerable code deployed on servers, on Lambda functions. And maybe we have some dependencies which are vulnerable too. Similarly, we can have co-permissive IAM roles, and we can have insecure environment variables. Now, these lead to broken authentication, rate limiting the views at times, and also malicious intent. Then the third category, what we see here is the platform misconfiguration. Now, oftentimes, what we do is we create resources. And when we are creating resources, there could be some set config drift, which we also observe. That could lead to disabled logging as one of the examples. And also that leads to some similar risk in terms of network segmentation. Now, when we talk about disabled logging, that refers to failed forensics. That refers to probably the EPC being misconfigured. And when we talk about lack of network segmentation, that also would lead to resource exhaustion. Now, the other two categories, what we see here, are kind of subcategories to the already explained ones. For example, the CI/CD risks are part of the functional level vulnerabilities, where we talk about the third-party package injection or the compromised build pipelines. And the monitoring gaps are very closely related to platform misconfigurations. There we talk about the no real-time monitoring and limited observability.
All right. So in this slide, what we have tried to do is that take the first three attack surface vectors and map it with the OWASP top 10 vulnerabilities. OWASP is the Open Web Application Security Project. Starting with the first one, and probably the most important, we have mapped platform misconfigurations with OWASP top 10 category 1, which is misconfigurations and broken access control. The image here, the T-Rex, it is a playful note on the recent T-app data breach that became the epicenter of one of 2025's most alarming data breaches. Essentially, hackers exploited an exposed database on Google's Firebase platform that they were leveraging on the backend and leaked over 72,000 user images, including selfies and sensitive photo IDs like driver's license, along with other unique user identifiers. The stolen data was subsequently dumped on a popular platform, 4chan, that sparked a frenzy of doxing, harassment, and potential identity theft, inviting incidents, inviting loads of class action lawsuits subsequently. It is also a wake-up call on the serious implications and pitfalls of expanding the scope of white coding at a system design level as well. Because it turns out that the founder was somebody who had sort of white coded the app, and he was an MBA graduate. Not to say that MBAs are not good coders. Still. Next, we move on to another perennial favorite vector of attackers, and which ranks third on the OWASP top 10 vulnerability list, the injection attacks. This category is essentially when untrusted data is sent to an interpreter as part of a command or a query, tricking the application into executing unintended commands or accessing data that it should not. And we map this with the trigger and event source risks in the context of serverless environments. The image on the slide, with the shattered move and minimized cloud peering through, is a not very subtle reference to the move it transfer vulnerability, which was a serious SQL injection flaw that did in fact terrify security teams globally throughout late 2023. Imagine the move it transfer as a critical file transfer application, which was widely being used across industries for securely exchanging sensitive data via the SFTP and HTTPS protocols. Attackers discovered that by injecting malicious SQL code into web requests, they could not only extract massive amounts of data directly from the underlying database, but in some cases, even achieve remote code execution by dropping web shells onto the server. In a serverless context, while we might not have traditional SQL database directly tied to every Lambda, injection risks still persist in the form of event triggers and event source risks, as mentioned in the earlier slide. Third, we shift gears and move towards the vulnerable and outdated dependencies. This is category 6 in the OWASP top 10, and we map this with the function level vulnerabilities in the context of serverless architectures and attack surface. In the development world, where we assemble functions from a myriad open source libraries and packages, the risk is extremely amplified and is often with blind spots. The image of the slide is a vivid callback to one of the most impactful software vulnerabilities in recent memory, which is the Log4j, specifically the Log4j exploit discovered in the Apache Log4j logging library. This wasn't just some obscure flaw, rather a critical remote code execution vulnerability in the most widely deployed open source programs in the world. The reason it resonates with Minecraft is because the game servers were the first ones to be hit with as a consequence of the exploit. And the game servers, which were primarily built on Java, used older versions of the Log4j, the logging library. And when the vulnerability became public, attackers, including those looking to deploy crypto stealers or gain initial access, very quickly targeted the Microsoft servers. They found that by simply inserting a specially crafted string into chat messages or server names, they could trigger the Log4j exploit, leading to unauthenticated remote code execution. This meant they could effectively take over the server, install malware, or perform other malicious actions, all because of a single vulnerable dependency. Now think about it for a moment. A ubiquitous logging library embedded deep within the supply chain of countless applications, including gaming servers, could be exploited so easily. And in the context of serverless, every Python pip install, every Node.js npm install, and every Java Maven dependency brings with it a potential supply chain risk, exacerbated by its significant cascading effects across each player. Moving on, let's talk about something that often gets the management's attention, which is the money aspect. We've established that serverless isn't a silver bullet and the responsibility shifts, but what's the tangible cost that responsibility isn't met? If you look at the chart, this illustrates the rapid, almost exponential growth of the serverless computing market. We're talking about a market that was over 19 billion in 2024 and is now projected to exceed $76 billion by 2030, with a compound annual growth rate of 23%. Now, this isn't just a trend. It's a fundamental paradigm shift driven by benefits like reduced development cycles and a faster time to market. A huge portion of this, over 61%, is driven by function as a service, or FaaS, and hence we often use serverless and function as a service interchangeably. And I sort of wonder that it's a favorite amongst even the medium, small, and micro enterprises and early stage startups, precisely because of these cost savings. That growth, however, also magnifies the risk. If you look at the next chart, this is where the security rubber meets the road. Projected losses due to serverless-related breaches. Now, this isn't just a direct damage. This forecast also incorporates cascading secondary losses that may include investor losses, insurance, legal and settlement fees, reputation damage, PR management, and any external consulting costs. Now, obviously, as the serverless market grows, so with the losses by associated security incidents, which is what we have modeled into by taking three scenarios: base, high, and high plus. Even in a conservative base scenario, you see a significant uptick in the projected losses, growing from tens of millions to well over $100 million by 2030. Then we stress test with high and high plus security uplifts. Those projected losses push past roughly 1% of the entire serverless market by 2030. Now, a question for you is, based on what we have discussed till now, what gaps and vulnerabilities do you think are associated with serverless architectures? That could be anything. It could be even like in cloud computing in general. What we would request you to do, you can scan the QR code and you can put your replies, and we'll move on to the next our tech, and we'll come back to this later.
You can take a minute.
Yeah.
You can take a minute here, and people, please feel free to scan the QR code and type in your answers. The moment you start typing in, you'll see the answers coming up here as well. This will be a fun activity. If you want to spend some time, we can do this, and then we can move on with the slides. Let's see, we got a participant typing. Oh, is it you, Nimish? I don't know. So when we say serverless, I hope you guys are aware of what serverless components exist on cloud today, like the Lambda functions, the SQS, SNS, DynamoDB tables, specific to AWS, right? And something very similar in Azure, in other places as well. So think about those, think about what kind of vulnerabilities we see there. Oh, all right, we see something coming up already. Variable leaks, denial of service attacks performed in large scale. Correct.
Variable leaks can also be a good attack vector in terms of, especially if you're modeling
It's
AI models.
absolutely, it's like unsecure environment variables for Lambda functions. All right, if input validation is weak, attackers can inject payloads into those triggers. That's a good one. Insecure coding practices. Yep, absolutely. Well, thank you. I think what we'll do is the code will be open, but we'll move on to the next slides in the interest of time, and we'll come back to this probably at the end. So what we also did is we kind of have a case study here where we wanted to have a home lab environment setup where we could a little bit investigate the attack scenarios, the defense for something on serverless cloud, right? So what we did is we took an example of an AI workflow, and in the next slide, we'll show you what the architecture of the home lab environment looks like, and we'll go through each component one by one. So the project name is called Links Lab, and it's available on that GitHub repo there. If you could scan that, and if you want to kind of contribute to that, we are open for contributions as well. So what we want to project here is how using a free AWS sphere, you can use some of these services which are part of the serverless components again, and how you can build an AI workflow. And in this example, we are showing how sentiment analysis can be done when a user passes it a review comment, and the output of the comment would be like whether the sentiment is positive, neutral, or a negative. So in this case, we are taking some components here like the Lambda function, the secrets manager, the API gateway, the bedrock model itself, which helps us with the sentiment analysis and the SG bucket. Now, when the user comes in, they call the API to get the sentiment of the particular review. What happens in the backend is you have an authorizer Lambda. The authorizer Lambda helps in authorizing the user and gets them the correct role in terms of accessing that API. And based on the checks which happen in the backend, then the worker Lambda calls the bedrock model in turn to process the request coming in, which is basically the sentiment analysis model, right? So for this, we have used Llama 3, and we can use any other model from available in Bedrock as an option. And we can change those models as well based on the needs and based on the examination as well. Like we have conducted sentiment analysis, we could do anything else as well. Those things are pretty configurable. And finally, what we are also doing is we are saving those requests in S3 bucket and storing it in one of those files there. So this is the overall architecture of Links Lab. And now Nimish will walk us through the attack scenarios and the corresponding defense for some of those patterns, what we already spoke about in the slides.
All right. So now this modified diagram highlights some critical attack vectors and the risks within the very same workflow. We revisit the three scenarios which we talked about earlier, and we have now mapped them in the context of our own model. And I want to draw your attention to the first, which is platform misconfigurations on the top left, leading to failed forensics. And if the authorizer Lambda, due to any platform misconfigurations, returns a deny policy to the API gateway, we end up losing observability of incoming requests to the Lambda function. Now, this at its worst can create a catastrophic blind spot. Our security teams lose crucial forensic data about the malicious request, the full payload, the specific intent, the originating IP, or any contextual information that the worker Lambda would have processed and logged. Now, this isn't just a loss of logs, it's a loss of the ability to conduct full incident response, to understand the attack, and to prevent future occurrences. It's a failed forensics scenario. On a function level, moving on to the function level vulnerabilities, leading to leaked secrets, and that's at the top right. Even if the authorizer allows the request, our Lambda functions themselves are not immune. A function level vulnerability, perhaps an injection flaw like we just discussed, or a vulnerable dependency within the worker Lambda could lead to leaked secrets. Now, this might be API keys for the Bedrock model, the S3 credentials, or even secrets for other internal services pulled from the secrets manager. If an attacker gains control through remote code execution or by exploiting a vulnerable library, those secrets are their first target, allowing for subsequent lateral movement or data exfiltration. Last, trigger risks leading to malicious inputs. These are the bottom left. The user's input to the API gateway is not just a benign sentiment analysis text, as is in the case of our model. It represents trigger risks and the potential for malicious inputs. This could be command injection prompts, the SQL injection payloads, targeting a database further down the workflow, or even prompt injection attempts designed to manipulate the model's behavior, which could be to extract training data, elicit sensitive PII information, or even bypass content filters. Now, without these robust input validations at every layer, these malicious inputs can trigger unintended actions or exploit vulnerabilities deeper within our workflow. In summary, a simple platform misconfiguration, such as the deny policy, doesn't just block a request. It can create a black hole in our security telemetry, leading to failed forensics and masking potential resource exhaustion if a denial of service attempt, as somebody rightly mentioned, even as a title question, repeatedly hit the authorizer lambda without being properly monitored downstream. Now, this demonstrates that the serverless security isn't just about securing code. It's fundamentally about securing the configuration and the interaction between these highly decoupled and ephemeral components.
Also, again, the repo here also has documented a couple of these scenarios, like how do you simulate these adapt scenarios. So if anybody wants to also add some more scenarios, please feel free to look into the repo, reach out with a pull request, and be more than happy to kind of contribute that in the model, because that is expanding. We are also planning to do some more future work in terms of experimenting with other cloud providers. That's something, an ongoing research which we are doing on the side. And just a disclaimer, we are not representing our employers today. It's part of our something which we find very interesting in cloud security space, and that's what we are presenting here.
You just say that so that you don't go and search about an employer. Exactly the exploits that they have.
Right. Want to go to the next screen?
So the final takeaways and best practices, we kind of summarize the presentation so far. Serverless doesn't mean tools.
Exactly. You still own identity, data, dependencies, and configurations.
Faster deployments, faster disasters.
Not at all. You need to enhance your production pipelines via structured velocity.
Isolation wasn't just a pandemic thing.
It is not, because security is a blast radius management. You need to isolate by function, by the account, by the VPC, and by the tenant.
Trust boundaries matter. Validate inputs, isolate events.
Rightly said. You need to validate schemas at the edge and keep your handlers small and unimportant.
I think it's working. It is not a real strategy.
It is not. You need the traces that follow an event across the services and logs which can be queried later on.
Lastly, you lose the server, not the responsibility.
Serverless changes the shape of risk, and your job is still to design for failure. That's all we had, guys. And we're up for questions. Next slide. There are some details on the slide. If you want to connect to us on LinkedIn, these are our socials. And we are here for questions if you have any. We do have 5 more minutes. We appreciate any interaction.
Thank you, guys.
Thank you.